welcome back. I'm the chair for this next session. I'm very pleased that we're going to be hearing about the most important astronomical country in the world, not Chile, South Africa. South Africa's like that. So first up we have Rosie van Moreya, who's going to be talking about South African astronomy in the era of large telescopes.
Thank you very much. Okay, so this is actually, I'm presenting on behalf of SARAO and SAO. And apparently, like everyone else, we went through a name change as well. So we used to be SKA Africa. So the big SKA square kilometer radio telescope coming, we are a partner in that. And we used to be only a project, and now we've merged into the NRF as a facility. And one of the best things I can say about that is that our new color scheme is this faded blue, okay, which is slightly better than the Dayglow orange. Although I have to say, if you're out there in the middle of nowhere, it makes you detectable if anything goes wrong. You know? But just to give you an idea, South Africa, yes, we have a lot of problems. Let's be honest about it. But in terms of astronomy, we are probably one of the fastest growing countries. We have an optical part. This is the one we all know and love. This is Sutherland, where we have SALT and the other smaller telescopes. And we have a lot of partner telescopes on the plateau as well. And the one thing we should notice between this one and this one is all of those are independent telescopes. This is Meerkat, Meerkat being a radio telescope that is one. Multiple components of one. But radio astronomy is probably, I think, one of the more transient geared astronomies. And that's because radio astronomy is a software-based astronomy. So we collect signals, and we can combine them at will if we know what to do with them. So you can have Meerkat in a 64 array, you can have a 32 array, you can have a single dish and a fly's eye array, you can have a beamformer, you can have a correlator. So let me translate native, my speak, to astronomy. Radio astronomy, we work on frequencies. We are at the longer, very long wavelengths. So Meerkat has L-band, UHF coming online, she has L-band, she'll have S-band, she'll have X-band. What that translates to is wavelengths of 30 centimeters, 15 centimeters, 7 centimeters, and 5 centimeters. So please keep that in mind, because I'm going to translate back to native. We have some shares between, obviously, Meerkat and Sutherland, and one of the big drives for South African astronomy is multi-wavelength. So we all know that, okay, so optical will be that tiny little spot. This is just a jet, okay, just as a physical jet in the galaxy. And this is what the optical will see, okay. There's a X-ray counterpart and this big blob here, and that's the radio part. So radio, you will have heard, is called blobology, and that's exactly what we see, blobs. In the optical, you can actually see there's spirals coming out, and you can see them slightly here in the Meerkat, and that's actually indicative of polarimetry. Okay, so both optical and radio can do polarimetry science. One of these circles is the primary beam of Meerkat, so we have to do a couple of pointings, mosaicing to get all the information. But you can see the power if you actually put all the sciences together. Okay. Now, this is the nice selling point. This is what you present to people if you want them to give you money. Okay. What you don't tell them is all the hidden nastiness below. So you have two completely different sciences, two completely different processing methodologies, two completely different instruments, different modes, different astronomers, different ways of processing and capturing data. Okay. And generally, those all have to be will have to be developed. So big growth in transient domain type astronomy. We all know that is the new field where new discoveries is lying. Okay. You have increasingly large survey facilities. SKA is going to be a survey facility. Meerkat is largely a survey facility. The data rates in these big telescopes make it of the order that you will probably have a pipeline for radio. You will not have raw data. I'll get to that a little later. So you'll have these alerts going out. You'll have alerts coming in where you want to find if there is a counterpart identified, identifying a counterpart, following up, all those kind of nice things you can do. So if you think you have a problem only in optical, we're going to make it 300 times worse by introducing all the new surveys and multi-wavelength. And then all of these instruments are wide field. Okay, brilliant for detecting transients. You want a wide range of objects, a wide time scale. So for Meerkat, currently we're working on nanosecond time scales as quick as we can go. That is a hardware limit because of our maser timing clock. Okay, if we can get better, we'll go to picoseconds. And then obviously, you have to tie both ground-based and space-based facilities. So, cooperation, collaboration, cooperation. Two different sets of the same coin. And what we found in South Africa is that geographic co-location, okay, is really a plus. So, this is SAO. This is Soraya, and there is Liesbeek Parkway. We are 500 meters from each other. Okay? The engineers, the software programmers, software engineers, and the applied scientists like myself. Okay? So I'm not an astronomer by training. I'm an astronomer by conversion. We actually do walk across this road quite often. Depending on the project we're working, we will have desks on both sides. After the open call last year, when we had the first imaging call for Meerkat, we did actually start getting more astronomer collaboration, and that's simply because now the science is becoming available. Spectroscopy translates easily between radio and optical. Radio just captures the spectrum by default. That is our input. Okay, while optical, actually, you have to go through hoops and fancy instrumentation. And then the transient beamformer that we would call, those two are more native. The photometry imaging side difference between them, there I'm having some problems finding something that really does map between them. They are two distinct beasts. So except for identification, there's not much I can do for you. So that's the Cape Town. That's where we all live. We like Cape Town, all right? Up there in the Northern Cape, where there are no people, literally no people, you have one person per 2 square kilometers. Nice, no people. There are the two facilities, Sutherland, the Plateau, and the Meerkat Big Array. Those two facilities are 200 kilometers apart, and the Google Maps yellow is really not nice, but there's literally a road between them. Okay? They see the same part of sky, they're close by, and because of legacy. So the people who used to build SALT moved over to build Meerkat. Okay, people who used to work in SALT and we're working in Meerkat. Okay, so we have a natural integration and sharing of knowledge, and it's simply because of accident. Okay, of the history of building telescopes. So the new kids on the block. That's where we're going to focus. There's a lot of old telescopes. There's a lot of legacy software. Okay. But any older system, you will appreciate, has a lot of work to actually make them, well, even just automated. So SALT and Meerkat, they are 100% queue scheduled. Meerkat will do service scheduling. We prefer that. Unlike optical, we don't like people on site. Meerkat works in L-band. Guess where this works, right? 1 gigahertz. We make it really, really, really uncomfortable for you on site, even for ourselves. So we are remote. We started off remote. We also started with the newer, because we're now, Meerkat's now 5 years, so we're actually really operational. we have the newest technologies, the best of everything. Okay, so we're actually ahead of the curve slightly. Sold some legacy, like they're still XML. We're fully JSON, but we started off that way, so that's our luck. Variety of instruments and modes. Okay. Optical, you have to build the instruments. Meerkat, you just have to build an antenna. So Meerkat, when I choose to observe, I tell her which identity she should take. She acquires herself, she configures the firmware and software, and she does that observational type. Having simultaneous observations is not a problem because I just have to tell her to output both streams, please. Okay. So rapid instrument change for us is not actually instrument change. It's a software reconfiguration. So it's slightly easier for the Meerkat than it is for the Salt, but both of them can handle it fairly quickly. Scheduling and monitoring and different cadences. At the moment, both are queue scheduled by default through a user. So the poor staff astronomer and the poor operator or technician, they sit there and literally take care. We are working right now at updating all our schedulers so that they do actually move towards the phase when they can be more automated. Then it becomes more of a babysitting job to evaluate if it is the next observation is actually valid also. Then the operator and the astronomer actually does more of a human function. They evaluate the quality of the data rather than getting the telescope to do work. So that makes a lot more sense in terms of data quality. And then also in terms of injection. So if you have a short notice follow-up or you have a TRO or something like that. So we currently on Meerkat can do a TRO turnaround in 5 minutes, and that's simply because we have to set up the schedule because we're not automated, so humans are slow. So all these things will improve as we move forward. And then obviously the one thing that will benefit is our target of opportunities, transients, and those kind of things. This is just natural from having everything automated. Now, radio astronomy, optical is nice because if your wavelength is the size of an amoeba, okay, a mirror is good. If you have something that's larger, you need more space, and that's simply because your detector, which is basically your mirror, will grow to capture the wavelength. So for UHF, you just have the basic dipole antennas and those. So the netting there, because the wavelength is so long, obviously it becomes a reflector. Okay. So these are the Euro guys. They do the epoch of reionization. They push down into the frequency space. So that is then going UHF, VHF, and those things. This is CBAS. This is CBAS South. So we have a northern counterpart. And this is obviously C-band. So this is now your 30 centimeter. And then Meerkat, she has, depending on what you want, she has various, she has a carousel that can change your wave band. Currently, L-band is the standard UHF. So that's the other thing. L-band is very noisy because we have satellites. Every time they launch a satellite, okay, we lose a piece of bandwidth. So that's less science we can do, okay? And these things of Google, no, they're going to launch this network of small cube satellites. And we go, oh, hell no. Yeah. And then the VLA had one the other day, so they had the new RFI detection, this Roomba, you know, they know exactly where it's going. It's a new paradigm. We have to be there. So the more efficient communication becomes, the higher the frequency space they want to invade. So things that we used to be safe at isn't safe anymore. But, oddly enough, all the analog bands are abandoned now because there isn't analog TV anymore. The big satellites are redundant. They're not broadcasting anymore. So if you are looking at the epoch of reionization, you want to go back in time to where the Big Bang is, okay? Your passband is clean. So you get some, you lose some, okay. Then obviously the epoch of reionization, as we go down in frequency, the wavelengths do actually increase to the size of a football field. So that's large, which is why the square kilometer will literally be, the SKA will have the coverage of a square kilometer in order to detect those waves. You can see why South Africa is one of the best places to be at the moment, because there's Meerkat, we have Hardraw, there's the AVN, which is the African VLBI, is repurposing telecoms, abandoned telecoms satellites to give us more. Okay, they are all C-band, so now we have L-band and C-band, UHF. We're doing well. So if you get past those, you start to bind them up with your optical. All right. Now you have so much option. And this is the part that really, really, really is the best part. Problem is, we don't have money to appoint a lot of software engineers. They're fairly expensive, especially if they're good. We are science institutes, and the NRF it carries it .ac.za. We're academic. We're non-degree granting, but we are academic, therefore public funded. My job is to train people and then see them go to finances to get a better salary than mine. That's okay. I can have them for 3 years. But in spite of all of that, and only having a handful of people really, really, really working on this, I think what we have done and the way that we are going is very positive. So SALT, obviously, they have to do a lot more work. So they have to put in the detection devices. They've started in 2016. They actually have to, so they've allocated a lot of time for their TOs and those things because for them it is disruptive. For Meerkat, as I say, we are more geared towards multiple types of observations. You have your standards, but your time domain and your transients comes more easily. So we have Meer time, which is basically testing gravitational fields and radiation. We have Thundercat, which is looking for new types of standard transients and new types of transients. Right now, this is my biggest problem because they trigger TOs on a daily basis. And then you have TRAPM, and they are the people who are looking for more exotic. So TRAPM is pulsar-based, so they're looking for more exotic types of astronomy phenomenon. And obviously the FRBs. And 2 years ago, we did actually get an FRB, which is a fast radio burst that is repeating. So we do know they are natural phenomena. Well, they didn't used to be, they are now. So you can see that in the standard approach, Meerkat is already there. Manually working with our optical counterparts, we can set these things together. It's inefficient. And then the new kids on the block coming online now is commensals. Meerkat has MOUs with institutes to keep watching at all times. Commensals are exactly what they are. It's my domain. I am quite happy there. I get all the data all the time. The problem is when you are commensal with Meerkat, you are facing the big data problem now. So Meerkat outputs data, full rate, in L-band. We sample at 1.72 gigasamples per second. If we capture full rate at, so I think BFI has been updated to a 4 terabyte SSD. That gives me half an hour of data capture on a single antenna, and it gives me 10 seconds on the entire array. So that's why we say pipelines, all right? Even your processing will be on the data side. Your standard data size from a slow Meerkat observation is 100 gigabytes, right? You're not downloading that. And then, so most of these guys are trying to slow down data rates, so, averaging and those kind of things, you can do that. And then as soon as they have a detection, that's the only time they will output. Now, if you have a nanosecond detection, 10 seconds is a lot of time that they can do processing. So FPF views are 1,000 beams. They literally form, follow, and observe and process. All of these guys obviously have racks of data. So we're talking about 16 racks, canals, 20 to 40 servers for every one of them. And then breakthrough listen, which is they take in the already data set, rechannelize it further in order to look for very narrow signals. So obviously this is your, your techno signals, let's put it this way. So that is fake signals, that's not natural defined to be. But it also, for someone like me who dabbles in masers, very useful because they're a very narrow natural phenomena. Obviously, we're not doing this alone. So those are our partners, PIs. For Meertam is Matthew Bales. Thundercat is Patrick Vogt and Rob Fender. Trapman is Ben Stappers and Michael Kramer. And Breakthrough Listen is Andrew Simeon at UC Berkeley. For SALT, also, you have multiple partners and graduate students. But why stop there? So in the next 3 years, we're going to make our lives much more difficult. Meerkat, first part is built. We're fairly certain she's going to work. The other, she can do science while we build the rest. That's fine. So through Max Planck and China, we have received funding and is now been signed that we will build an extension. So the longest baseline for Meerkat is 8 kilometers. I'm going to put in a few more antennas in there, give a 20-kilometer odd longest baseline. So your primary beam goes from, your synthesized beam for resolution goes from 7 arc seconds to 1 arc second, which is brilliant for resolution. You retain your core for sensitivity, okay? And then we tie all of that up because there's going to be surveys and L-band and S-band because we have so many antennas, multiple of them, simultaneous, okay? Software, no one cares. Tie them in with our optical counterparts, SALT, SAO. Already, David is LSST partner. We have the Meerlicht. The Meerlicht follows in the night, Meerkat. She's a small telescope of 1 meter. She identifies an optical counterpart. No use putting SALT on a system, okay? Because SALT is a big system. You want to know there's something to follow up on. So smaller telescopes are very useful because they can identify counterparts. And you have Monet South, and you have your big, and Meerkat Hess. I got an email this morning because I'm one of the astronomer AUDs, that they are actually now converging on a schedule for simultaneous Meerkat Hess observation. So that's very, very nice. And then if you look at this, so this is something that David drew up for the transients, Monet, Meerlicht, and those things. And what you see here is alerts, VO events, some mastermind doing that. Can anyone see a Tom obviously popping out there? Okay. So that's when Rachel, I don't know how David got to Rachel or how the two got together, but and they sent over this piece of software, and I'm like, whoa, I don't need to code this. Okay, so that is just so, it's a natural fit. Obviously, we still have to do a lot of work, okay? But you can see that we are moving exactly in this direction. And the biggest problem now is actually just taking the human data. So the thing that humans work completely different. And dissecting that into the Tom structure. And for this, I actually do want to thank Rachel and David personally for the patience of helping me disseminate my knowledge into a Tom structure. So obviously, you have your identification part for your alerts, which you will have to plug into. You have your planning part, and then the thing that, so we will have to write SALT alert systems. And then also the thing is on the planning part and the science requesting part, SALT has this annulus, you know. She is a segmented mirror, so she only moves in azimuth, can't tilt in elevation. So she is an annulus. Meerkat, because of the various bandwidths, the higher frequencies, if bad weather comes in, we move to lower frequencies. Meerkat is always on. She does not stop. Nothing can stop her. L-band, I don't care about the weather. Okay, so that's kind of like a satellite. It's very nice. And then this is just, so this is the Thundercat guys. Okay, so they, oh God, on a daily basis, you get these kind of things where they say, this is an alert, just take your best setup and give us what we want because we know her as good as anyone else. So a Tom in there instead of me getting the email would be appreciated. Thank you very much. And that is it. I mean, I don't have a lot to show in terms of applications, but hopefully you can see the potential. And we're open to anyone who wants to play along, okay? And If you have any questions, I'll take them. Yes. Which is why for us to start, while we are now, well, things are changing in terms of the intelligent observatory, the way we actually handle these things, and the Meerkat, which is new. It makes sense now to talk to all these people and say, what do you have? Instead of isolating a system and later realizing you can't actually plus there's a lot of useful software out there, okay? So finding overlap and synergy and seeing how you can collaborate, okay, that is key. And we are lucky enough that we are in the stage of beginning, okay, which makes it so much easier. So yeah, that's exactly what we want.
I want to ask a question about music.
Mm-hmm.
So I noticed, how much is it actually gathering what Meerkat is?
As soon as you can see, she follows Meerkat. So at night, Meerlicht will track all the targets that Meerkat is observing at that time. So those two commensal at all times, yeah. But she's dedicated to it, so we just need to make sure she knows exactly where we are. Now, the thing we need to get going is her triggering something so we can get the rest of them on there. Mm. So Meerlicht is not one of my sciences. That's a UCT project. I am unsure if there is any. I haven't seen any published. So I won't, unfortunately, be able to give you those. But you can email Ewan, so he may be able to give you any examples. But as I say, for me, I don't know. I don't get those data sets, preferably. And because it's not published at the moment, I don't think we have any public domain. But I may be under correction there. Meerkat's primary beam size is 1 degree in L band. So if you go up to X band, you lose about 45%. So then it obviously shrinks down, but it's still a fairly large primary beam in terms of your if you want to scatter beams in her. So that's you can really see a great patch of the sky.
Yeah. My life story is from South Africa to the UK.
Oh yeah, there we go.
And even to the northwest.
Yeah. Okay, fantastic. Right. Yeah, let's just do which of the. See. Oh, that moved.
Yep.
Okay. Great. Okay. Yeah, big thank you to Rachel and the LCO team for kind of working with me, doing a bit of work, getting me started with stuff. If anybody doesn't know, I'm from Liverpool John Moores University, working with the Liverpool Telescope. So the talk is going to cover kind of what we've got at the moment and what our model's been for the last 10 years in transient astronomy. Some of the technical aspects, but then the second part is looking to the future and the plans that we've got for a new 4-meter telescope and how that's going. So just a little bit of background. We're part of the Astrophysics Research Institute at John Moores, and we're one of the largest with about 100 kind of people on site in the UK. And we're kind of unique in having our own 2-meter facility. It's not a model in the UK that's very common. For you to own your own facility, it's much more kind of consortiums owned. And all UK astronomers kind of have access, but we'll get onto that. And where we are is just in the observatory Roque de los Muchachos in La Palma. The Saharan desert causes terrible kind of havoc with any computer or fan elements that are moving sometimes with the fine dust. And we're just on the very top of the caldera of a very steep mountain, the steepest kind of island in the world. You've got the 10.4 meter Gran Tucán, which is a kind of a Keck copy, which the Spanish run. And we're over on this side by the Isaac Newton telescope and the William Herschel telescope, the first telescopes to be on there. We're also going to have the Cherenkov telescope array in the future, and maybe TMT, which we're very excited about because they will increase the bend radius of the roads going up there, make some tunnels bigger, and that's going to make our job a lot easier, basically. So we're very excited about that. And here we are, the distinctive Clamshell Dome. And this was built as a spin-off company from John Moores University in the early 2000s. In the era of 8-meter telescopes, we were audacious. We said, who wants to buy a 2-meter telescope? And we focused on producing very specific telescopes for time-domain astronomy. The clamshell design dome is specifically because we want to be able to salute a target and get there and not have to wait for a dome rotating to make operations efficient and to follow up things quickly. So the model was always about efficient time-domain astronomy and a robotic control system built in from the very beginning of the project. So our instrumentation ethos is the other thing. We're a 2-meter telescope, we're small. You can actually see that the ethos is that we have small instruments. That's just a physical constraint. This is normal size power sockets, and this is the A and G box with octagonal shaped ports, so 8 around the sides and 1 on the bottom. So we can have up to 9 instruments, and with a science fold mirror that rotates between instruments, we can change within around 10 seconds between instruments. So very little overheads, especially for observations where you want to do spectroscopy and imaging, or polarimetry and spectroscopy. Efficient instruments, we haven't got a big aperture. They have to be high throughput. Also, being small, high throughput, small numbers of elements, they're quite cheap as well and quick to kind of develop. And then numerous is the last thing that we're after. So just what we've got on the telescope at the moment is kind of a workhorse imager, single band near-infrared imager, and specific high-speed exoplanet imager. And then 2 spectrographs, fiber-fed IFU. But this one here, Sprat, is using a CMOS camera with a very low resolution for very efficient kind of classification. And that's working very, very well. I think it's so small it was taken on as hand luggage, basically, on the flight out there. Then the other kind of niche that we have is polarimetry, and something that I'm very interested in. And we've been looking at high cadence polarimetry, so sources which are changing on the observation timescale need this high cadence approach where we're using electron multiplying CCDs and rotating Polaroids on the order of a couple of hertz, basically. Got MOPTOP, which is a prototype, a single band, which is going onto the telescope, and it's going to give us much higher polarimetric accuracy, and this is quite an exciting instrument for us. So overall, we're kind of an efficient telescope run on quite a small budget. We're in a maintenance phase now. We're not growing. But we have had some quite high-impact science, especially with GRB follow-up. We can be the first there. I think there was one GRB where we were on target, taking data within 90 seconds of the trigger, and the telescope texted the team. This was, before kind of Slack. So get an SMS, beep in the night. It was very exciting. So I've just advertised a fantastic telescope that the American community does not have access to directly. Hopefully you all want to use it. So there is some direct application through the PAT, which is the UK Time Allocation Committee. But I'm going to talk at the very end about how there might be changes to that model and openings. But through collaboration with ourselves at John Moores or Spanish institutions, we'd encourage that. Please contact us with science ideas. We can hook you up and put you in touch with people that can get time. The NSO, National Schools Observatory, 15% of the time. If your science is high cadence, GRI, of M51, M57, then you'd be in luck. But I'm not sure if you should be kind of collaborating with kids in school. So looking at kind of the system we have is a robotic control system. And generally we have scheduled observations, that's one mode of operations, and target of opportunity override. And those two modes provide enough coverage, we believe, to do all of the science goals. With high enough priority, you can get observations back within the hour with scheduled observations, or within 2 hours. Anything shorter than an hour, where decisions need to be made by a pipeline based on kind of what discovery magnitude there is, or discovery candidates in JRBs, we use TOO override. And this is the kind of scheduler. It's very, very simple, but that's mainly so that we can understand it. All it is 4 coefficients against the priority, current elevation, condition matching, and then just a random, just so we don't get one target always blocking out another. And we don't look into the future. Just at any time, we analyze all of the valid observations for that moment and those conditions, and we score all of those and execute the one with the highest score. So this is the model we have, and the group here is the analogous to the LCO request. So a group will have timing constraints. We can do kind of a flexible window, or we can do repeated kind of phased observations, observing constraints, and an observation sequence, which can include one or more instrument configs and one or more targets. The access to this, it was great a few years ago, a phase 2 Java access. It's quite manual and clunky. And so actually the Tom Toolkit and speaking with the team has been really exciting for us. And the way that we're making it, is the RTML access that we have. So quite an old kind of language, completely analogous to the modern JSON payloads that John was talking about. And we've got this available for IOO, IOI, our optical and infrared images, and our low resolution and higher resolution spectrographs. And it is the mechanism that we use for target of opportunity override, which it was mainly developed for. But this is RN, and this is an XML document. It contains all of the information in a less human readable format than JSON. David's been really good at kind of working with us, and we've updated something on our telescope side so that we can do this in a Pythonic way rather than using Java. And we have now basically submitted observations to the Liverpool telescope, and they appear. And now the Tom Toolkit and a module that's hopefully upcoming will be alongside Growth, which is already using the RTML-based payload and communications for the Liverpool telescope. The slight issue that we have is that you send your RTML payload over to the telescope, it comes back and goes either reject or confirm. That's it. That's all you're getting. The API doesn't have this bidirectional interface that our phase 2 user interface has. You can't query what have I submitted to the telescope, how much time have I got left on my proposal. You can cancel observations, so a bit clunky, but with the Tom Toolkit, it looks like the only way that we could modify an existing observation would be to cancel the one we've sent over, amend and resend. But that's something that we're looking at doing. And it's been actually just very easy. We kind of talked about this a number of months ago, and I hadn't done much. But I just looked in 238 lines of code in a single kind of facility, lt.py facility file. We've created a observing form, and it creates the XML payload and sends it over to the telescope. And this kind of really fast development has been absolutely brilliant. So we're excited in working further with this and integrating more functionality. Hopefully, the phase 2 will be closing the loop and pulling data from our data archive. So that'll be a second test of the flexibility using kind of our older API standards. That's where we were now, but the new Robotic Telescope is the exciting thing. This is going to move the Liverpool Telescope forward. This is going to move us from just a maintenance phase, where we've just got enough money to operate, or in some cases not quite enough, to developing new ideas, new systems based around this new telescope. So we know the challenges. The scare stories that astronomers are telling their children at night is 10 to the 7 alerts. That's going to go down. You know, as we're categorizing main belt asteroids, we'll see, and cataclysmic variables, there's going to be a dropping of that. But it is an issue that the fire hose era is more than we could ever follow up. So the need for kind of efficient follow-up is one of the big things that we're pitching for with this telescope, and for our own science as well. So our proposal, obviously, if you want to follow up LST sources, is to build a telescope on La Palma in the Northern Hemisphere. But it's not so bad. The reasons for that is we know the island, and we're working with the Spanish. They're very big contributors to this. So we are going to have a 30% kind of simultaneous sky overlap with ZTF and LSST. But also, non-simultaneous, we can follow up anything kind of north of LSST's zenith. At slightly higher air masses, but we're hoping that there will be enough alerts that there'll be easy enough work for this telescope to be getting on with categorization. And these are the partners that we have at the moment. We are kind of speaking with other people about mirror manufacture, but we're bringing the expertise of robotic operations, of the data reduction. The IAC, who operate Grantacan, bringing kind of instrumentation and segmented mirror skills. This is going to be a bit of a shock, the next slide. University of Oviedo, they worked actually with Astafeto, who built the LSST structure, and one of the options was for us to have a smaller LSST scaled down, but the costs are quite large in scaling down 8 meter. But they're going to work with Astafeto with some design reviews and work packages there. And we've got the Thai National Observatory that we've done quite a few projects in kind of control hardware and modern EtherCAT bus systems. And they operate at 2.4 thing. So our team at the moment, we've got 6 full-time in the UK and 4 full-time at the IAC. So we are moving forward with our Phase A design for this telescope. And this is what we're looking at. It's a successor to the LT. We believe that the observational model is successful, but we want 4 times the collecting area and 4 times the slew speed. So for gamma ray burst science, we want to be on target, taking data within 30 seconds of a trigger, which, is really pushing it. But General Dynamics, that we've spoken to, who built kind of a SAW, Vista, DCT, they didn't balk at the idea. They just said we need to go to direct drive on the AS, and we need to kind of block some of these direct drive motors to get that torque. And we need to do kind of vibrational analysis and the eigenmodes of the structure. So, getting there might be achievable. Taking data, we want the settle time to be less than 10 seconds or 15 seconds. Or we could probably just start taking data anyway, and the first bit will have a bit higher noise. So what does a 4-meter mirror give you? So we can go deeper. If we're looking at gamma ray bursts, the Liverpool Telescope is 2 meter. We don't reach the peak of the sample. But with a 4.2 meter in yellow, it's not showing up, we can actually get beyond that peak. That's one thing we can do. We can gain fuller samples of certain objects. Or we can improve the efficiency. Very diligently, I said, well, if we've got 5 times the collecting area, what does that do to the exposure time? Put it into a calculator, it's a 5th. When you're out of the read noise dominated overhead, basically. Yeah. So the location that we've got and the concept design is going to be next to the William Herschel telescope, 4.2 meter, that's going to become a survey telescope probably 100% of the time. So the UK community is losing a 4 meter class facility for kind of flexible science and moving to this multi-object spectrograph weave. On a site that, we've is a decommissioned site of an old telescope, transit telescope. The instrumentation that we want, standard and high-speed imager. would be common. We want a polarimeter. We're good friends with GASP, Galway Astronomical Stokes Polarimeter, which is an instrument which could find a permanent home on our telescope. And then the big thing we want is an image slicing IFU spectrograph. Now, I spoke to my colleague this morning, and I didn't believe him. I think this is silly. 14 by 10 arc-second IFU. The idea of this is if our pointing model is good enough, we can blind acquire onto targets 90% of the time. You know, that's kind of the goal within 30 seconds. And I do see some smiles around the room because people are kind of in disbelief. But, you know, it's an audacious idea. Oh, you already have? Oh, fantastic. Oh, okay, great. So, yeah, this is what we're offering. Kind of very, very able to respond quickly to triggers and to have very high efficiency with smaller overheads. The blue and the red arm of our kind of concept design for the spectrograph with the image slicer at the front. And it's a very small instrument. This is a 20 millimeter scale here, and this is a 50 millimeter scale here. So again, it's carrying over our ethos of small instrumentation. How am I doing for time? Ooh, rushed through it a bit, actually. So current work and where we are with the project, we've got our enclosure and site concept design sorted, and we're doing kind of CFD analysis on the structure to get kind of a first order approximation. And we're looking at kind of the wind loading analysis on the tube structure to work out the wind oscillations and work with kind of the provider of the telescope to provide that data. And we've kind of identified potential suppliers for our enclosure, for our telescope structure, for the mirrors as well. And we're in the process of putting together, doing some surveys, site surveys, and putting in our planning application. So this is the current plan at the moment and milestones. We've already completed our Phase A design, and we're into work package definition at the moment. Early next year, we're hoping to sign partner agreements whilst we're doing site surveys. And then as we get kind of planning permission at the back end of next year, then this is where we can pull the trigger and greenlight the project, where we can pull the trigger on getting the mirrors manufactured. The IAC are hoping to build a mirror grinding facility for segments. This is what they're very interested in. And we've also got the people that made the TMT segments in China wanting to offer us segments as a contribution in kind. The plan would be that we'd be kind of on sky for first light mid-2024 with operations 2025. I mean, we've all seen projects, haven't we, kind of at our stage with kind of timelines. So I'm sure it takes no imagination to say it's going to be a little bit further over here. So the funding status, and you really have to forgive me for this football analogy, we're third and three at the moment. Basically, we're 70% of the way there in the funding puzzle, and we had a grant last year which didn't come through, and that would have green-lighted the project. We would have probably had things in the process of being ordered right now had that grant come through. But we've got very strong operational support from the STFC, and the model is that our partners might contribute quite a bit, but then when we go into operations, the operations cost is put onto STFC. So the recent developments with kind of the change in the funding models for LSST are of interest here. The subscription that LSST UK kind of had ready to buy into the LSST project is no longer required, and the LSSTC are looking for contributions in kind. Primarily, the first kind of thing that they're looking for is a cost reduction, so farming out critical kind of jobs to different partners. The second thing would be maximizing kind of scientific exploitation of what LSST is going to provide. And this is where we're trying to make a case that a 4-meter efficient follow-up facility is, going to be maximizing the science. So that's what we're hoping, and we're hoping that essentially the STFC, with money that they put aside, that this could could be one of the ways which will kind of solve this funding puzzle within kind of the next 12 months for us to be on time scale. So kind of the takeaway points of the talk, it would be, just to try and speak to the American community and get more usage. One of the models we're looking at and offering is time actually on the LT and American representation. This is just one option on the time allocation committee of the PATS. So the 30% of the time, there'd be American representation on that time allocation committee, and it could be available to the American community. So please, if that's of interest, do make some noise for those kind of ideas. If there's anything more immediately that you want access to the telescope, please do speak to us. We will be able to find you collaborators internally at the Astrophysics Research Institute or elsewhere with other users of the telescope. And also, if there's any groups that are interested in the new robotic telescope, we are very open to new partners who might be able to bring ideas, but mainly money. And the name of the telescope is provisional at the moment. It's not going to be called the new robotic telescope. We don't know what it's going to be called, but naming opportunity is there. A few million, we'll call it whatever you want. So anyone with, we are kind of there, yeah. So that's it. That's my talk. Just for information, if you want to kind of see the telescope, the links are clickable in the PDF, so do that. Anything related to the Liverpool Telescope and observation now, contact Chris Copperwheat, who's the astronomer in charge. Anything to do with the new plans for the robotic telescope, and even if it's just to say this is the kind of science I want to do and inform our kind of design decisions, please do that. And that's Helen Jermack to speak to. So yeah, thank you very much.
Scope, you meant scope face?
Yeah.
Okay, questions for Doug?
It is now okay. So for what order of magnitude partner contributions are being looked for the new telescope, and for the Liverpool telescope, is there any way to gain access by purchasing time?
Okay, so the first one of that, I can give you an order of magnitude by saying that the thing that would have green-lighted us was a £7 million grant that we would have received. It had to be match funded, and then there would have been 5 million going into our high performance computing group. So kind of the synergy there. So we're looking at that kind of order of magnitude. For the Liverpool telescope, I would have to speak to my director, but certainly people have bought time on it. For example, constraining the orbits of Gaia with ESA. We were providing kind of follow-up and astrometry of the Gaia satellite for it to help it constrain its orbits during 6 months of the year.
I just wanted to shout out that the Liverpool telescope, when integrated into the Growth Marshall, was one graduate student visiting for 2 weeks, and it just works beautifully. I mean, there's been no surprises. I mean, basically, we've been able to trigger automatically on our highest priority targets. The data gets reduced, flows back into the Growth Marshall. Very seamless, very beautiful, lots of great science and great papers. So this is a very nice and
the Growth Marshall is
system.
actually the application that we had. It was just Kirsty McTaggart, who's a PhD student, and she came over for a couple of weeks to work with your developers. And yeah, this has been quite a big success story, yeah. Oh, yeah.
Quick question. So, the dome design that you're doing, I mean, you want it tied to the telescope because you want it to be a very rapid response. So, the enclosure should be able to be as fast as the telescope is able to move.
Yeah.
Otherwise, you lose any fast response that you
Absolutely,
build
yeah,
into the
yeah.
telescope. Yeah.
Yep. So we're, as I understand it, in the early 2000s, the kind of the dome speed would not have been achievable. We're speaking to M3, who have put people back onto La Palma because they're going to be providing TMT dome, and they also did DCT. And they haven't run away from us, basically, at this idea. You know, these speeds can be achievable. There's a cost implication with it, but they're just saying it's just more torque, basically. And potentially lightweighting of the dome can also help with that, yeah.
So when we've tried to increase the dome speed on the 48-inch, we ended up with shredded rubber on the floor. So
yeah.
There are some mechanical things you have to take into account.
Yeah.
We need better quality tires on the
Right. Thank you.
Okay, so more questions? Thank you, right there. Okay, I think so. Now is a planned demo of how to write an Antares filter.
Can I disconnect? Right. So thank you for your interest. So just want to show you how to write a filter. So to start, you probably first want to do. So I believe everyone has registered to the Antares. If not, please do so. So on the Antares web page, here you can click to see strings. So once you go to that page, you'll see different kind of strings here. So this is what we are currently actively string out. And say if you want to go to one of strings, like for example high noise ratio ones, then you can see here we group each alert on the same position of the sky. We call it locus. So if you click in the locus, then you'll see the light curve here, like this one. And they also have different information here, so you can check. But I probably don't want to go to individual ones, so that's why we try to use Time Toolkit. So here. You can see your Antares button here. So if you click that one and say, okay, I want to query a stream, then you can say which kind of stream you want. For example, I want to this one, and then I just say SNR, submit. Then you'll see it's in your stack of streams here. So now I guess it's probably you're not satisfied with just our, predefined strings. So that's why it brings us to how to write your own filters. So if you go to Antares webpage, there's a place called FAQ, and here it will show you how to start use Antares, especially how to write a filter and submit to Antares. So you can just click this link. In principle, it will take you to the next step, which is you have to use our wonderfully designed science platform. And then if you are there, you will click here and see, okay, there's quick start, and then use the Jupyter Notebook so you can do all the codings in Python. And then once you launch the Jupyter Notebook, it will take you to this directory. And here we have some contributed notebooks. So this one, the latest one, which was updated a while ago. the contributed one. All these are in the FAQ, so you can just follow FAQ to find it. And here we have this Python notebook. So it will basically walk you through all the steps, how to define your own filter. So in principle, you just follow these steps. So first of all, you need to connect to our test database. So we have a small database with a small number of alerts you can test against, so it doesn't cost you too much computation time. And then you need to do some imports, just like other Python codes. And after that, and then connecting to the our test database. After that, we have a template showing you how to write a filter. So this is one example. So if you don't really want to dig into detail of that, then maybe it's easier to start with some of our strings. So here is one. So the high synchronous ratio one I just showed you. So you can go there and see, okay, it's defined some synchronous ratio, and then get some properties from the locus. And here are some parameters that we get from CTF. So you can use those parameters to define your filters. And then at the end, you will define which kind of string you want to send out. So here we use high synchronous ratio. So this is a unique name which will appear on our website. Okay, so once you've done that, say you have finished writing your string, your filters, you want to test it. So you can first say you find alerts which you really like and then want to test. You can give it alert ID here, and then you can just run this line, shooting your filter here, and then it will run on this alert and then give you the results, see if it passed the filter. You also want to test over several alerts, and it can be done here. At the end, if you are satisfied with the results, then you can go to here, our Antares webpage, to submit the filter. So this will require that you register to Antares. So, and then you go to the Antares website, and then there's a filter page here. And then you can see the other filters, the open ones, and then you can click Add. Then you just put in the name of the filter. We prefer that you provide a short description, so that when we go through the code, we can see if it's follow the designs you desired. And if there's a bug, then we know how to help you fix the bugs. And just copy paste your code here, then click Submit. So I think that's all to walk you through. And again, if you have any questions or problems, you can always start with the FAQ page here on the Antares website, and then it will guide you through how to do all these steps. And that's all from my side. Maybe Wes first.
Yeah.
Oh, yeah.
So just looking at the predefined streams, and of course mainly paying attention to the solar system stream for myself, I had noticed when you clicked on an alert that really the only information that seemed to be available in the alert was sort of the brightness and the location, brightness, location, and time.
Yes, so for these streams, we actually get everything from CDF. So I think besides the location and brightness, you should also be able to get like the transient names, I believe. Like here, these are all the properties. We also have the properties from JPL horizons. So we can also get those probably like orbital elements there.
Where is the trend? That was the name I was looking for. I couldn't find it.
So it should be I think it's let me check. It should be the SSO confirmed.
But not. Oh, okay. That might have been the candidate I was looking at.
Yeah. So
all
candidates could be different, but we can discuss later. James.
So just to clarify, at the end you said that do you vet our code before it gets added? Can you just talk more about that step at the end? You said something about...
Sorry, I didn't get you. So.
Oh, sure. At the end, I think you said that somebody on your side has to vet our code just to make sure it's doing what we think it's doing.
Yeah.
Can you just talk more about that step?
Yeah, sure. So, let me check. So this part, so I think you were mentioning about this one, right? So after you submit, then it will be sent to us, especially to our software engineer. So what we'll do is that we try to test again. So using the same test database and see if it runs or if it crashes. So if it runs without any problem, then we'll just assign a new filter to that. So it's mainly just, try to make sure that the code doesn't crash.
And I believe there are currently 3 deployed user filters in Antares, and
yes.
there's been a couple more submitted recently as well.
Yeah.
So I have a couple of practical questions as a user who might potentially want to contribute a filter, for example. My question would be, what kind of hardware do I have what kind of hardware resources can I call on to have this filter running at your end? Because potentially users could write a filter that has some kind of massive overhead, some really computationally intensive thing that completely snarls up the Antares hardware and just crashes everything for everybody. So what kind of limitations do you have for that? And the follow-on question to that is, if I, as a user, write a filter that works fine initially, but then after some change, or at the survey end perhaps, or at the Antares end, somehow depreciates or breaks, how do I find out what the error is, and how do I debug it?
Sure. So the first question is about the computation resource. So I believe now we have computer clusters with, I think, 5 machines and maybe minimal CPUs. I don't really have that number in my mind. So, but in principle, if you can test against the data lab dev kit and then it works fine, then what we'll do is we'll try to, so that's again about our fitting mechanism. So we'll go through your code and then try to put it a test. And then if it's wrong within a certain limit of time, then we'll put it in our current pipeline. If it's not running, then we'll let you know. So it's probably running too long. And then our software engineer will tell you which part is wrong, and then maybe you can try to, to take or try to shorten the computation time. So that's the first one. The second one is whenever a filter is online, then it will send a notification to our Slack channel. And if at some point there's error, it will also send an error message on the Slack channel. So we'll know what's the problem. And if we identify the problems, we will also notify the users who submit this filter. And besides that, you always get a chance to update your filters. So we prefer, if you are kind of revising your filter, if you can say this is version 1, version 2, then that would be great for us to do the version control.
So thank you. Just to follow up on that,
sure.
One thing I've found very useful in code of this kind that I've written before is to have logs files output by the software that are then accessible online, maybe on a contributing user dashboard of some kind. Is that a possibility?
Yeah, so we do have some monitoring or log software to do that automatically. So that's how our software engineer check if the system is running correctly. I'm not sure if that's easily acceptable to the users, but we do have the logs. So if there's a problem, we can always, pass those logs to the users so we can better debug your code.
Thank you very much. I can imagine this being a really powerful way for users to contribute going forward.
Yeah.
Any more questions?
Okay, so we're going to give you the opportunity to enjoy sunshine. So early lunch. So back here at 2 for the afternoon session. So let's thank the speakers again from this morning's session.
One question. Are the filters accessible only to the people who submitted them, or are they generally accessible?
So yeah, we can discuss about that. So
I mean, if you had a...
favorite is public, but if you prefer to stay private, which I totally understand, it's also, yeah, we can read that.
Okay, just curious what the default is.
Yeah, default is not, but I totally understand because people doesn't want this as to school, so that's a big problem. And we only force